Hello, and welcome to a webinar that Southface is putting on, talking about the differences between the two different commercial energy code compliance options, ASHRAE 90.1, 2013, or International Energy Conservation Code, IECC 2015. And either option is allowed by code. Both are acceptable. But, when you adopt the IECC, you automatically also adopt the ASHRAE 90.1, and they go in pairs. So future codes will be the 2018 IECC and the 2016 ASHRAE 90.1. They work as a pair. My name is Mike Barcik. I'm a technical principal with Southface, and I just want to make a plug for lots of good energy code resources that are available at southface.org. And the sort of the easy way to navigate to them, excuse me, easy way to navigate to them is click on education, and under courses there's energy code, and Georgia Energy Code has a whole bunch of stuff, including a document that we're going to push hard at the end called the Commercial Energy Code Field Guide. So you can go there and download it for free, and we'll have a slide on that at the end. Can I introduce you? My colleague who will add color commentary, or play-by-play is me, I guess. Joey Starr. Joey, you want to introduce yourself?
Hi, I'm Joey Starr. I'm a project manager here at Southface. Primarily working in residential, but I'm going to sit in here for a commercial and learn a little bit from
Thanks, Joe. Okay, so make things click and move forward. That would be more impressive if we could advance the slide. There we go. We got it. Thanks. That's your job, Joe, to make good things happen. Our organization has been around for over 40 years, and we focus heavily on the built environment and have been involved with energy codes for decades and decades. So we try to stay on top of what's happening on technologies that make sense. Our basic goals are really, as mentioned, are to try to explain and understand the differences between the two codes. They are similar. They certainly have a comparable scope, but there are a couple important differences between the two. And as a designer or constructor team, you have to make a choice. You have to go one path or the other, and it's also all or none. You pick your pathway, and then you got to stay on it. You can't do envelope compliance under one code and then lighting under another code. So you got to stay consistent. We'll try to make sure this is we'll try to make sure this is covered correctly and understand how it applies in construction projects. And we're not really going to get to demonstrate it, but we are going to strongly encourage you to use this free tool, ComCheck, which is an excellent tool to help demonstrate compliance with the energy code. So let's dive on in. And the first thing, I just kind of want to give the basic layout. The IECC is broken out into two parts. The first section is commercial. The second section is residential. And that residential would be like 1 and 2 family and low-rise multifamily. We'll talk more about that. ASHRAE 90.1 has very similar scope, but it's broken out into sections. So or chapters. Chapter 5 is envelope, 6 is HVAC, water heating, lighting, and so on. Most of the sort of meat and potatoes of the Commercial Energy Code and the IECC is the envelope requirements and the mechanical and the water heating and lighting, and they're all under Section C4. Both of these codes offer an option that if you can't show compliance with the prescriptive code or with a simple trade-off using ComCheck, you do have an out, and that's an energy simulation model. And both of these codes allow that as an option. So it's called total building performance under the IECC. It's probably better known cousin over here in the ASHRAE world. It's called the energy cost budget approach. I have, in my experience, never seen a project use the total building performance, but I know many projects, particularly those pursuing LEED, are quite often following the rules of the energy cost budget method. So we'll drive on. And here's a great kind of visual way to look at the code, to consider the code. In every section, there's always going to be mandatory requirements. These have to be met, There's no trade-off for these. You got to do them. There's also envelope and lighting and mechanical requirements that may or may not be prescriptive and offer trade-offs. Kind of depends on what's happening. But particularly with envelope, you find, and the codes align really well on this, that you can follow the prescriptive chart, if you will, from the IECC, or the equivalent prescriptive chart for ASHRAE 90.1. And we'll talk about it. You will see it. You pick your climate zone, and you basically, the way I would describe it, Joe, is it's a recipe, and you follow the recipe, and nobody gets hurt. You know, you can sort of put more sugar in, but you don't want to put less sugar in. It's sort of a minimum recipe. So that's kind of the way that works. If for some reason there's an aspect of this commercial prescriptive option that, you know, is hard to meet, you can often do a fairly simple trade-off where you're going to use a tool like ComCheck, which is definitely your friend, and you'll sort of over-insulate one part of the envelope, and that will allow you to do something less somewhere else. So, you know, maybe your glazing is not quite meeting code, but you put extra insulation in the roof or whatever. But that's a great tool for showing that. And again, ComCheck does a really good job of, we'll keep pushing it, but it really does a good job of not making you do as much math, and it provides a really nice printout and kind of a paper trail for the code department. If you can't make it work with that, you do have the whole building simulation option, which both codes have, but that usually involves paying someone to help you. So you know, it's typically a more complicated project that's going to do that. And then we'll dive in and kind of see how this goes. So ASHRAE has a definition of what defines a conditioned space, and cooling is just a fairly small amount of BTUs per BTU per hour per square foot. Heating is actually somewhat climate zone dependent. It's anything more than 5 in climate zone 2, more than 10 in climate zone 3, and more than 15 in climate zone 4. But that's really not a lot of heat. And so if you put a small amount of heat, you're pretty much going to probably be over that threshold. You're a fully conditioned space. ASHRAE also has one extra thing that the other code doesn't have, which is a semi-heated space. And we'll talk more about that, but I would really think a better name for that would be freeze protected. And then I didn't mention, but if it's an indirectly conditioned space, that means the space is inside the thermal envelope. That's still, you know, conditioned space. Examples of unconditioned spaces are things like, you know, a vented attic space or a open air crawl space or a open air parking garage or something like that. So when you go to ASHRAE's tables for prescriptive code, you're going to see that the vast majority of projects, commercial buildings, are going to fall into this non-residential column. If the commercial building has somebody sleeping in it, a residential component, then it sort of has a separate column, and then a very likely not seen a lot freeze protected option. When you go to the IECC, a change was made in terms of the definition of conditioned space. Georgia just more or less lined it up a lot more with ASHRAE. But similar concept. And they have an exemption if your building basically uses almost no energy whatsoever. You're exempt from code. That's probably, you know, an unconditioned storage building. And the big thing is their names for the two. They don't have a third type. They only have two types. They have either, you know, Group R if people are sleeping in it, or All Other. So that's your choices. Excuse me. Very quickly, here's the sort of substituted definition of what is conditioned space, and again, it lines up pretty well with ASHRAE. Excuse me. What are we talking about? What has to apply with code? Basically, new work. New work needs to meet code. Build a brand new building, everything in it is new, everything in it needs to meet code. If you renovate a building, the parts that you're messing with and the part that you're touching, that usually needs to be brought up to code. And if you get into like an alteration, you go in and you put in, lighting or relight a building, they want you to bring that up to code, for example. So generally, just remember, new work needs to meet code. And if you're not sure, always have a conversation with your code official. So we're going to talk about the building envelope. And I won't read this, but I will mention, oh, by the way, Joe, did you know that long before Tesla had solar shingles, Southface had solar shingles. These date back to the 90s, and they lasted about 18 years. I think we finally pulled them off. But anyway, the codes basically offer a little bit of guidance for the code official, on how to apply in a alteration, retrofit kind of situation. But again, more or less, I'm not going to read them, but it says if you add storm windows to a building, you're probably not bringing them up to code, but you're making them better. So we're not going to regulate you there, especially, and they want low E storm windows. If you mess with a cavity in an existing building and there's already insulation in it, we're probably just going to not worry about it. And the other thing is that generally with glazing replacement, take a look at each code, and they have sort of different approaches with glazing replacement. The IECC, kind of says the weighted average exception can be applied. ASHRAE says if you go in and you do up to 25% of all the glazing, all the fenestration in a building, then as long as you don't make it any worse, you're okay. But if you want to, replace half the glass, in either case, you're going to have to bring it up to code. Okay, so again, emphasize again, you must pick your pathway. Choose one code over the other. And the IECC is, I would say, one subtle difference is it's probably a little more succinct. It's a little more rigid because of that. It doesn't offer you as much sort of design flexibility. ASHRAE kind of gives you a little more wiggle room on things in general, but there's probably exceptions to every statement. No clear winner. Both codes are very good. Comply with both codes, you've got a really good building. Or either code, I guess I should say. So the main part under envelope is there's three main areas: insulation, fenestration, and air leakage. So I think it's pretty obvious, but you're going to need to figure out which climate zone you're in. Most of the South is either climate zones 2, 3, or 4, and everybody kind of on the more sort of on this side of the Mississippi or ish is in zone that has a letter A, which means a moisture heavy zone. B is a dry zone, that's out here, and C is, I call it the Seattle zone. That's what I call it, the marine zone. The only other interesting thing here is that there's a very poorly named line, this line, white line right here, that sort of subdivides climate zone 3A into, above is apparently below it is warm and humid, but above it is not. I really kind of resent that implication, because it's pretty warm and humid above it, but that's their terminology. I think a gnat line is a better name for it, but there's not too much that really affects this. I think there may be one or two small things like economizer exceptions here above and below, but really, for all intents and purposes, you can ignore that line for the commercial code. All right, getting into the envelope, I'm guessing most people are fairly comfortable with this. Joe, can you explain how are the R value and the U factor of the assembly related?
I believe they're reciprocal to each other.
That's right. So
that's a fancy word I learned in school.
that's a fancy word, means the inverse, right? So if we want to have a high R value, we want to have a low U factor. And the code basically says you can meet a prescriptive R value, or you can come up that is at least, whatever this minimum number is, or you could meet a prescriptive U factor for any assembly as long as you're not higher than a certain sort of threshold. So you could sort of think is, R values are minimum, U factors in the code are speed limits. You can't go faster than that, or you got to stay below the the threshold. The other big thing is percent glazing. The IECC really wants to limit glazing prescriptively to 30%. ASHRAE gives you a little bit more with 40%. You can go higher than that. A lot of commercial buildings go higher than that, but they're going to have to do some sort of trade-off. You could do some amount of trade-off probably with ComCheck, but if you're really trying to do a building that's 75% glass, you're most likely going to need to do an energy model. This is something new in this version of the code, is that in certain spaces in commercial buildings, this really good idea, which is to provide natural daylight, is now going to become a requirement. And I say required, you can always do trade-offs, but they're really pushing you to take advantage of natural daylight in certain spaces that sort of, let's say, are ideal for that. We'll talk more about that. One example of how the two codes kind of, they have similar performance specs, but they don't have the same language, is metal buildings. And we kind of jokingly say, metal buildings just kind of have their own code. They're off doing their own thing, and that's probably the easiest way to look at it. Walls of a metal building in ASHRAE are a continuous, almost R10. That's what the CI means, continuous insulation. The IECC prescriptive option is a R13 in the cavity plus a R6.5 continuous. Or, in either code, any wall assembly that meets a certain U factor. And we'll see that later. Likewise, on roofs, ASHRAE says an R10 plus an R19 filled cavity. That would meet the code. And both codes are very big on having this thermal spacer block, basically so that the metal of the roof doesn't touch the metal of the purlin. The IECC has different language. They say R19 or plus an R11 liner system. And here's some examples of some different different manufacturers' technologies. Or either code can be satisfied by anybody's assembly as long as the U factor is met. So here's just a picture again of a manufacturer. They've got different systems. They've got different, sort of their nominal R30 system with a single layer or crossing layers, that kind of thing. Some of these may be referenced by the code, but they all have a U factor associated with them. Okay. Speaking of U factors, probably one of the most valuable things that comes out of ASHRAE, it's not in the other code, but the other code uses it, is Appendix A, which has tables and tables and tables that look really exciting, don't they, Joe? But you got to think that somebody has made these tables because basically you do not have to do the math. You do not have to look up or calculate, or you do have to look up, you don't have to calculate. And actually, if you take our advice and use ComCheck, it does the lookup. So you just build your assembly and it will determine the U factor for that assembly. That is a very wonderful thing about having ASHRAE be a part of this equation. And issues, we're playing in the big leagues here, issues like thermal bridging are really critical. You might put R13 in the cavity and have a steel stud, but the reality is an R13 in a 2x4 16-inch on center cavity, the effective R value is not 13. It's actually less than half of that. It's only 6. So as you can imagine, the code is very strong on having us use a thermal break of continuous insulation on the outside of steel framing. It's not impossible to trade that off and go to just exterior gyp, but you don't want to do that. That's a lot of heat flow going through that and very susceptible to a moisture problem too. So you're going to see that the code is going to require more insulation outboard of the steel studs, and that's a good thing. So if you can't meet the prescriptive amount, at least have, let's say, R3, something there. But the code, you'll see what the prescriptive amounts are. Again, I think we've covered this, but very quickly, if you're a commercial building that does not have people sleeping overnight in it, most commercial buildings probably meet this criteria. They have different names in different codes. If you are, you're either called Group R or you're a residential commercial building. What a great name. And only ASHRAE has this option, which says we can potentially put just enough heat to keep the pipes from freezing, but it is not much. And in my climate zone 3, 10 BTU per hour per square foot is not very much. If you have a 5,000 square foot warehouse, you would be allowed to have 50,000 BTUs of input of gas heat. That's one very tiny hanging gas space heater. And I guarantee the designer is going to say, oh, no, I'm going to hang 8 of those. And that's just to knock the chill off. So it's really to keep that space at 33 degrees from freezing. Okay, so very few applications of this, and you got to get approval. All right, let's look at insulation. Insulation, a couple sort of basic things that these come out of ASHRAE, but there's sort of comparable ones in the other code. Insulation components generally need to be labeled. You have to follow the manufacturer's requirements and install them correctly. The only exception there is that they recognize that fiberglass is going to get compressed in metal buildings, so they acknowledge that and recognize that. Insulation has to be in substantial contact with the air barrier. Insulation, that is a key element, and a lot of commercial buildings fail on that. So the insulation ideally is fully encapsulated, especially if it's air impermeable insulation such as fiberglass. Insulation has to completely fill and cover the area. They limit you on a scissor truss application. You can't use loose fill if the slope is more than about 3 and 12. They want you to use a bat or something else. Can lights basically need to be airtight, IC rated, or you can't compromise your air barrier and your insulation coverage. Insulation, this is a critical one. All insulation has to be protected from the elements. And probably one of the worst offenders on this is refrigerant piping that's up on the roof. I've seen some scary stuff there, or some very sad stuff. If you use multiple layers of, say, rigid board insulation sheathing, they would like you to stagger the joints. That makes perfect sense. All right, so what is the code? Well, for Climate Zone 3, here is the code. I'm going to put a little box around most commercial buildings fall under here. And the insulation assembly method you choose dictates a different prescriptive R value or a different prescriptive U factor. So if you put the insulation above the roof deck, the answer is 25. And that is highlighted in yellow because anything in yellow is something that has changed from the previous energy code. So in Georgia. So it was 20, and now it's gone to 25. But that is still arguably the best place for roof insulation. Or you can do any assembly that has a roof insulation up there as long as you get an 039 or lower U factor. Likewise, metal buildings. If you do an attic situation, my pointer runs away. An attic situation, it's R38 prescriptively, or any assembly that has a U factor of 027 or lower. Likewise with walls, a mass wall, concrete, cinder block, R7.6, or any assembly that is a U factor of 0.123 or lower. And if you did the math, if you took 1 over this R value, you'd get something very close to that U factor. It's not exactly because there's some air films. The metal buildings, this is the U factor, this is the R value approach. Steel stud walls, R13 in the cavity, R5 continuous insulation. I'll just slide on down and just say here's the rest of the stuff. No basement wall insulation requirement, different R values for how you do your floor. Slabs don't need to be insulated unless they're radiant tubing in the slab. That makes it a heated slab. Very uncommon in the South. And then fenestration doors. The other climate zones have some, a little less R value typically over here, a little more R value in a colder climate zone. And note that sometimes you'll see, I'm going to go back to climate zone 3. Here's just an example of where there is a difference between the walls. If you're a mass wall and you're a standard commercial building, you only need that much continuous insulation. But if you're a residential occupancy, they want more insulation. Residential buildings tend to be more skin load dominated, so usually a little bit more insulation required in the shell, or a little lower U factor. So that's an example of, you know, the difference between the two types of assemblies. When you get to the other code, I'm going to jump on down. It's very similar. It's got, you know, sort of and there's climate zone 3. It's got all commercial buildings except for the residential ones. You can see it's got fairly comparable R value requirements, R38 again, R25 continuous. A little bit higher R value requirements on metal framing. So that's one example of where the steel framing, instead of R5, it's R7.5. And again, just slightly different numbers maybe. The only amendment Georgia made to the code, Georgia only amended the IECC, never amended ASHRAE. ASHRAE is just straight across the board, and that makes modeling simpler. But the only amendment here is that in Climate Zone 4, we're not going to require slab edge insulation. That would be for all commercial buildings. That's probably a little bit hard to justify. So let's kind of go into roofs. Where are you not allowed to put insulation on the roof, Joe? Yeah, drop ceiling tile. This has been banned in ASHRAE for 20 years and in the other code for at least 15. And everybody, this is just something that doesn't work. Most of us have seen this. We've got a lot of existing buildings that need to get fixed because this just does not work. It's not continuous insulation coverage. It's certainly not airtight. And it just has all kinds of air quality issues. So don't do this. You can do it for acoustic reasons, but it absolutely won't count. And we don't recommend it. And if you're, you know, just appreciate we're going to have to fix a lot of existing buildings. What you are allowed to do is put a hard ceiling and then put insulation above that and kind of maybe have an attic space or maybe not. But, you know, this is going to be an R38 in this example. And it's subject to failure. It's got issues with thermal bridging. It's allowed by code, but it's not the best place. A pretty decent option is to put, and this might be the fix for a lot of those existing buildings, is to come back and spray foam from the underneath side. You're probably not going to meet the prescriptive R38, but you know this approach is really going to work, and it gets every ducts are all inside, which is of course good, and it won't fall off, and it tends to be pretty airtight. So I think this is good. I have a little case study building I was involved in many years ago. Pretty small building, preschool, that they were going to put new lights in, and in the process of doing that, they're going to have to take out the grid ceiling. And I said, hey, why don't we get a quote on spray foam? And we ended up doing it. We did spray foam and new lighting. And then not too much longer after that, they were getting new equipment, and we calculated the load reduced by a third, which is pretty significant. So the cost of the spray foam really was offset by the reduction in the mechanical equipment, and much better comfort and air quality and all that. So where's the best place for roof insulation? Up on top, because it's continuous. It's very airtight. If it's not watertight, if it is watertight, it's going to be airtight. And this is certainly the way to go on a low slope roof. We definitely advocate for this. The only other thing that's kind of new in the code is that and a lot of people have been doing this anyway, is we really want to make the exposed surface of that be I'm going to call it shiny. Is that okay, Joe? That's a pretty technical term there. Shiny roof. A reflective roof is required, and it's a very good idea even in Climate Zone 4, but it's required in Climate Zones 3 and under. And a lot of the benefits of that may not seem as so obvious immediately, but one of them is obviously it reduces heat gain into the building, but often we put packaged equipment up on a building. And this unit is trying to dump heat to the outdoors on a hot day, and if this is a dark roof, the roof temperature could be 150 plus degrees. And it's a lot easier to dump air that's, to the roof that the air is probably 100 degrees on a hot day. So that's much more efficient. Not to mention a lot of times we're getting our ventilation air from up here. So that's important too. There's also a heat island benefit to the larger city, which is essentially, this is an image of Atlanta from, you know, the early 70s, and there's very little paving and a fair amount of tree canopy, and this is 20 years later of development, and you can see that, you know, sort of the downtown area, Gwinnett County was a very fast-growing county, lots of trees, lots of asphalt roads, lots of dark roof buildings, an airport right here. So Joe, I understand you helped research some very sophisticated heat island modeling for Atlanta. Is that?
Yeah, I think next year.
Do you have your results ready to pop up here? Oh, they didn't come up. Oh, it's all red. Oh, I thought we saw Atlanta all turn red here. So the trees are important. So are the paving that we use, and so is the roofs on our buildings. Okay, so the code is going to acknowledge that we need to put on the shiny roof, but they write a spec for it that you can meet. But they do have some exceptions, so I'll make that. I will share, this was kind of interesting. We went up on the roof of a dark roof building at noon. It was 90 degrees, and it was just a light gray ballasted roof, but I tell you, it felt like your face was on fire. It was so hot. This is in July in a building over at Georgia Tech, and they had a section of a tray of a vegetated roof, and we got an infrared image of it, and you can really see what an impact it was. So vegetated roofs count, solar panel roofs count effectively as being, you know, part of your reflective roofs. And here's the same, more or less, concept and same language that's in the other code. So the other code is pushing us to this same kind of performance criteria. It really does make sense, really has a lot of nice benefits. We don't have one. So the other thing I want to mention is getting into the fenestration section now. We're looking at limits again. 40% from ASHRAE, 30% from IECC, and certain cases where daylighting is quote, quote, required and limits on skylights, or more or less encouragement to use skylights, but you want to kind of, with skylights there's definitely an optimum. You want to use just the right amount to get natural daylight, but not too many to kind of have a less insulated surface. The only kind of subtle thing that's interesting is ASHRAE, their definition of fenestration is basically glazing. The other code includes opaque fenestration, you know, as part of that definition. So it's a little subtle there. Here's an example. This building has 10,000 square feet of walls and 3,000 square feet of windows and glass doors, so that would be 30%. So you could use either code to show compliance, and you're still prescriptive. And again, if you need, you know, 42% glazing, you could potentially still get there using ComCheck. In terms of the performance metrics for glazing, the U factor is kind of how well insulated it is. Lower is better. The tail wagging the dog in the south is really the solar heat gain coefficient. That's what it's all about. And a double pane low E window has a much lower solar heat gain than a clear glass or and a tinted window can also reduce the solar heat gain, but you'll see there's some limitations on the tint in the ASHRAE approach. So we want a low solar heat gain. Usually a low E window will satisfy that requirement and also help you be better than code on the U factor. So double pane low E is probably the overall technology we're looking for. There's a couple other terms that are important. Air leakage on the glass, that's another thing that's supposed to be labeled on the windows. It often isn't. And why do we put in lit windows? Because we want visible light. So we kind of want to have a low U factor, which is more or less conduction, a low solar heat gain, which is more or less radiation, and a low air leakage, which is convection. But we want to have a high visible transmittance, which is why we hopefully put a window in the first place. If you don't want light, maybe you shouldn't put a window, because the opaque wall is probably a lot better insulated than the window. So if you don't want the light, don't put in the window. I'm going to get shot for saying that. The architects are going to lynch me. Okay, so the basic, there's some default tables in the codes. you do not want to go here. They are terrible and you'll never pass code. So you really need a label. This is much easier to find in residential style windows. The challenge is commercial windows usually have brand X of the glass and brand Y of the glaze of the frame, and you have to get the two put together. So you got to kind of do a little digging on that one. Here's what ASHRAE says for climate zone 3. U factors, pretty doable, pretty easy to hit, and they have different performance targets based on the type of frame material. But the one that's not in yellow, because it hasn't changed, but it is really critical, is a low solar heat gain of 0.25. You can get that all in the glass, or you can get credit for overhangs or other approaches, and we'll talk about that. And then we're also going to mention this ratio of visible light divided by the solar heat gain. They want visible light to be a higher amount than the solar heat gain, and what that really says is they don't want you to use a super dark tint. That's really what it's kind of saying. A tint will block a lot of solar gain, but it'll also block a lot of visible light. Okay, and here's the same U factor values for the other climate zones, and note that solar heat gain is relaxed a little bit in climate zone 4, but U factors are generally more stringent. More cold climate, more hot climate. Those are the changes. ASHRAE 90.1 really does give you a fair amount of credit for permanent overhangs. And the simple calculation is this thing called the projection factor, which is simply how much does the overhang stick out, that's A, divided by the distance from the bottom of the overhang to the bottom of the fenestration. And so if A is 3 feet and B is 9 feet, your projection factor is 1/3. Whatever your glass, you come down here, and whatever your glass solar heat gain is, you multiply it by 0.74. So you're really taking a 26% reduction of your actual glass solar heat gain. And so I can't emphasize enough how much you want to use ComCheck, because it will do all this math for you, and ComCheck will allow you to trade things off so much easier than you never want to do this by hand. So use ComCheck is definitely the way to go. The other code gives you a little bit of credit for overhangs. Basically, they kind of break up the world in small, medium, and large overhangs. Small, basically no credit, solar heat gain of 0.25. Medium, a little bit of credit. Large, a little bit more. But I think you're going to find generally ASHRAE sort of gives you more design flexibility on that. Again, always use ComCheck, either code. The overhangs have to be permanent. These all would provide shading of the glass, but the canopy down here would not be counted because it's not really permanent. It does work, and it's a great idea, but it's not considered permanent. Okay, we talked about daylighting. If you can meet 3 criteria, then the code is saying we really want you to have natural daylight in the space, at least prescriptively. So first of all, your space has to be a certain big enough size, 2,500 square feet. So it's not a small space, it's a decent sized space. And it needs to be under a roof that the ceiling height is 15 feet. And it needs to have an actual roof above it. So, it can't have the next floor above it. So it has to be sort of easy to put a skylight up there. And then it also has to be a type of occupancy or space that really is conducive to natural daylight. And, lobbies and office atriums or open offices or conference centers, convention centers. These really do kind of make sense. Retail, that's another great example. The other thing is you don't have to daylight the entire floor area, but you do have to daylight at least half of it. And in general, they kind of write the code around you're going to do it with skylights or roof monitors, but you're also allowed to do it with windows. You can get 50% of the floor area natural daylight just from windows. That's perfectly fine. And Joe, what do you think the light fixtures in those natural daylit zones, how do you think they probably want those to be controlled?
Probably need a integrated sensor with daylight sensor.
Yeah, some kind of automatic lighting control. We'll see that when we get to the lighting section. But basically, anywhere you have natural daylight available, it really makes sense to have an automatic control, just like you said, that will take that light level down when natural daylight's available. And there are exceptions. I'm not going to go through it, but there's exceptions for this. And you can trade this off, but generally this is what you're being held against in the code. You know, again, almost identical requirements in the other code. You know, very subtle differences. Your roof, 2,500 square feet, at least 75% of the roof is 15 feet high. So, you know, a little, very subtle restriction, but quite comparable. Driving on here, the other big thing that's as we've mentioned, the general solar heat gain requirement of 0.25 has some sort of very important aspects to it. You can meet that in different ways. You can meet it with the glass itself. You can meet it with overhangs. There's a couple exceptions. You can also get credit for what's called dynamic glazing, one where you put a little voltage on it and it goes from a clear window to a tint or vice versa. And just a little bit more kind of nuts and bolts on this. ASHRAE also has something that the other code doesn't. This is really, I would say, more of an encouragement to the designer to try to lay out your building intelligently regarding the sun, which a lot of buildings don't pay attention to that. But you really want to try to orient your building so that the vast majority of your glass is facing south or north. And that allows you to much more easily get and control natural daylight into the space. So this is our building. You can see there's a lot of good glass on the south. You can't see the north facade over here. It's got a lot of light, a lot of windows as well. North windows, you can get reflected daylight in about 15 feet. That's about it. South windows with light shelves and shading devices, you can even get natural daylight kicked 30, 40 feet into the space. And then there are no windows on the west facade. You can't see it. This is the east facade. These are very small slit windows right here that have exterior shading. There's two windows that are pretty large over here on the east facade. They have dynamic glazing. So lots of great technologies to help demonstrate what that does to the cooling load is pretty significant. So we're really trying to be intelligent about it. You know, if you've got to design your building where your glazing is equally distributed on all four sides, you can do that. You're just going to sort of work up a little bit of a hill, and again, ComCheck is your friend. It will calculate that for you. Okay. The other, we already mentioned this, so I'm just going to skip it. But basically, the visible transmittance needs to be 10% more than the solar heat gain. That's, again, just so you don't use a dark tint. How much more can I say about using ComCheck? Well, first of all, it's really, really good for envelope, and it's incredibly good for lighting, and it's kind of for mechanical. There's nothing really to trade off on mechanical, so it helps you build a list. But it's a great tool. It's free. It's available from energycodes.gov. They have a downloadable version. They also have a web-based version, which is actually a nice way to share amongst team members. So I would kind of say, you know, you might have your electrical folks working on the lighting, and you can share that file with them with the web-based version. Otherwise, you have to email the file. It's probably simpler that way. If you can't make it work with ComCheck, you can do a simulation, but it's usually playing in the big leagues here. So you're hiring an expert that knows how to do energy modeling. This is where everything is on the table. Lighting, envelope, mechanical. It's sort of saying all BTUs are created equal. So that's an option, but you know, generally it's not one you want to have to do unless you're trying to show that you're better than code. Okay. Last thing is air sealing. Both codes kind of, I would say, approach this in a somewhat naive way. They sort of say, oh, if you build with one of these materials, you know, you're probably airtight. And that's a bit naive. It's really more about the penetrations. But they want you to build and have a designated, if you will, surface that is your air barrier, particularly in the walls. And it's got details about, our experience is generally it's penetrations and it's junctions in the envelope. That's where ugly stuff happens. So in terms of air leakage, there's requirements about glazing and doors and things like that, and loading dock weather seals and all this stuff. but you know, most commercial fenestration should meet this requirement. Vestibules is a very significant one. Vestibules are required in climate zones 3 and up in both codes. Basically, some of the fine print, but a vestibule is kind of like an airlock, and you know, the idea that you're help the building stay more airtight, even though people have to come and go, and there's some details on it, but there are some important exceptions, and the ones in green over here are consistent in both codes. There's a very important one in blue that I wanted to make sure pops up. So, you know, non-entrance doors, dwelling unit doors, revolving doors, those all sort of either exempt or meet the criteria, only in climate zones 3 and up. And this one in blue, it says, if you're in climate zone 3 and you are a 3-story building and you're under 10,000 square feet, you do not have to have a vestibule. And a lot of strip retail could meet that requirement, whereas that is not in the IECC. So if you love vestibules, you probably want to go IECC. And the IECC does include these other two. So just be aware of that. Vestibules are a big deal. I would also suggest that people tend to want to condition them. You're allowed to condition them. We try to encourage designers not to condition them. Really, just let it be a buffer space. When you condition that and the outer door's open, guess what happens to all the conditioned air? So they still provide some good, but it's much better, really, in my opinion, to very indirectly condition them or under-condition them. Here's, again, what I just said. The one exception that they do include in the IECC that's not in the ASHRAE is they allow you to have an air curtain. So there's an example of an air curtain on a kitchen door. So nice idea. Okay, and this was you'll get a kick out of this, Joe. This is a commercial building we visited in the summertime, and let me just say it was not raining, but they were over-conditioning their vestibule, and they were so over-conditioning it that the glass was below dew point, and it looked like the building was sweating on the outside, because it was. That wasn't rain. So you know, don't do that. That's a waste of energy. Can lights, we mentioned that, basically insulated, rated, and airtight if they're going to penetrate the insulation. Where do failures occur? You know, the most common failure point of commercial buildings air leakage is above the drop ceiling tile. And so that's why I really like when architects design, we're in one right here that has a drop ceiling, but it's a cloud ceiling where the drop ceiling doesn't run all the way to the wall. You can actually see up. I think it kind of keeps people honest, and you don't see giant, you know, leak paths there. And it gets away from people trying to use a plenum as a return. So lots of failures can occur, such as one we probably have all seen, which is water stains on a drop ceiling tile. That's not a plumbing leak. That's not a roof leak. That's almost always condensation from an air leak. Where is the ugly stuff? It's wherever the vertical plane of the wall meets the sloped or horizontal plane of this roof, and no one's going to ever see that, so who cares, right? Well, that is a huge hole, and that lets in tons of moisture, and that's what causes stuff like this. This is kind of cool. One thing I do like about the IECC is they actually acknowledge the option of blower door testing to prove airtightness. And this is something that we absolutely advocate for. It's going to make it into ASHRAE in the next iteration, but it's not in this iteration. But this is a way to sort of prove, it's an option to prove air sealing. We think it's really valuable. And when you do this, these are some buildings we leak tested, and they were in it was basically a shell building, but we were still able to pressure test it. And you generally measure it at multiple test pressures, and that allows you to know very accurately how leaky it is at the one you want, which is 75 pascals, but also to plot a line and know how leaky the building is at virtually any pressure difference. So you can really learn a lot, and you can also find the holes. All right.